Alright, so let's think about how we can view a Lie algebra as vector fields. I don't have too much to say about this, but basically here the idea is you can think about the linear transformation from Kn to Kn as being a way of attaching the image Ra of x, thinking of it as a vector, to the point x. Alright, so I should also mention, of course, we remember elements of GL and K correspond to linear transformations on Kn. We have this correspondence, right? So you could add another arrow here and say, well, that also corresponds to, vector fields, right? You think of this as attaching a vector field at x, and that vector, the vector at x is Ra of x, right? So a path in GL and K, what's that? Well, that gives us a family of transformations on Kn, right? Gamma from some open interval to GL and K. So I suppose you could think of that as, I guess there's a lot of different ways you could think about it. It seems like I could think of it as a vector field for each choice of time in there. Now, move along here. How does the path gamma of t above act on a fixed vector? So here we're talking about the family of transformations, all right? So how does that act on a fixed vector in x on k? So let sigma of t be r gamma of t acting on x, right? This gives us a path in Kn, and sigma prime of 0 is r gamma prime of 0 of x. So, and again, we think of r gamma prime of 0 as thought of as a vector field on Kn, where we're attaching the vector r gamma prime of 0 of x at each x. It tells us how the family of linear transformations gamma t moves x initially. So this tells us how x moves initially by this family of transformations. I'm not sure I'm really saying enough here for you to understand it, so you forgive me if it doesn't make a lot of sense. There's some nice pictures, and the punchline here about rotations and their connection to SON is probably a little bit more intuitively understandable. But we visualize gamma prime of 0 in the Lie algebra of GL and K as represented by the vector field r gamma prime of 0 on Kn. So, like I said, pages 73, 74 give a better discussion, including how you can see for an n by n real matrix in the Lie algebra, little SON of SON, big SON, the vector field, if you will, Ra, is perpendicular to the point. So it's like that. In other words, it's kind of like a rotation around the origin. Well, let me move along here. I could say more, but it probably wouldn't make it make more sense. This probably is a little bit more understandable since it's algebra. So here we're talking about the Lie algebras of the orthogonal groups. All right, and so I haven't proved that these are the Lie algebras of the orthogonal groups, but that's the order of business here. So it turns out that this can be proved, and that's what we're going to prove, is that this is the Lie algebra of the orthogonal group, big ONK. So little ONK, it turns out, is the matrices that have this A plus A star equal to 0. Now A star is sometimes used, it's called A dagger in some other places. It's the conjugate transpose. So in different cases it's different things. In the case of the reals, it's skew symmetric. In the case of the complexes, it's skew Hermitian. In the case of the quaternionic case, it would be skew symplectic. And let me just show you an example or two before we get into the proof that that is indeed the Lie algebra of the orthogonal groups. So first of all, here's U2, skew Hermitian. So that means just pure imaginary on the diagonal, and these, when you flip them over and conjugate, they should, if you add two such things, you add that to itself, you should get back to 0, and you can you can see that the conjugate transpose of all these is equal to 0. Like this, when you, well, it's symmetric, so you transpose it, it's the same thing, and then conjugate it, it's minus itself, and so this plus minus itself is 0, of course, so it's skew Hermitian. It's easy enough to check that those are skew Hermitian. All right, so that gives us a real subspace of the complex, set of complex 2 by 2 matrices. It's a 4-dimensional real subspace. In other words, U2 is 4-dimensional. Okay. Enough about U2. They've had their day in the sun already. Let's see here. Now, the symplectic group of order 2, the algebra is then allegedly, that's what we're claiming, it's these skew symplectic matrices. In other words, the diagonal elements are just sort of pure imaginary type things, just, with just combinations of the linear combinations of the versors, real linear combinations, and then these guys are balanced in a certain way so that when you switch their places and conjugate them, they add to 0 when you add two such things. And then you can count the number of free parameters here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that gives you that the symplectic group of order 2 is 10 real dimensional. Yet another example, SO3, we said it's skew symmetric, and so here's the typical element of little SO3, looks like this. Sometimes these are called infinitesimal rotations for, in connection to the story I was telling you about the vector fields. And here's a comment about that. A in little SO3, RA goes from Rn to Rn and has the property that as a vector field, RAX is perpendicular to X. So think about circles and radials and perpendicular directions. It's kind of like that. So here's the here's a lemma that we would want to use. For A in n by n matrix of the k, the following are equivalent. A is in little o n k. RA is, it's not exactly symmetric, it's anti-symmetric, right? I mean, minus pulls out here with respect to the standard linear, standard inner product, right? And then if you have the real case, then you also have that RAX with X is equal to 0. In other words, this claim here that the it acts perpendicularly. Now the proof is left to the reader because the current expositor is lazy. All right, so here's the theorem we've been waiting for here for 3 minutes. The Lie algebra of ONK is little ONK. Now the proof. Here's the proof. So first of all, I don't know if I really defined this carefully yet. Just to be clear, big ONK, it's going to be transformations such that they preserve their isometries of the standard inner product over K. So that just basically ends up meaning when you work out the details that A times the Hermitian, well, let's say A times A star is equal to I. Now, so you take a curve which satisfies this condition, you differentiate it, and then that's pretty much it, because when you put in gamma of 0 being the identity, out pops the gamma prime of 0 plus gamma prime of 0 star is equal to 0, which is to say that it's, well, that's all those conditions, the anti-symmetric, the skew Hermitian, and the skew symplectic is all covered in this one argument. Pretty slick. So, for the more interesting part, if we want to show the other inclusion, that means that we have to take an arbitrary ONK element, say A, and produce a path in big ONK through I for which gamma prime of 0 is equal to A. Our previous work on frac G, we know that it's a vector space, so it suffices to prove that there exists a curve that gets you each basis element. So we'll prove this case-wise, k equals to r, for example. This curve works. If you look at gamma ij of t, I won't go through all of the details, but if you look at this curve here, you can easily check that gamma of 0 is I, and gamma prime of 0 ends up being eij minus eji, which, by the way, are the generators of the Lie algebra of SON, little son. And so, and you can also show that this curve is in fact in SON. I leave that to you, but once you show that gamma ij transpose times gamma ij is equal to I, that shows that this curve is in fact a curve in SON, and consequently its initial velocity vector is a Lie algebra element in little son. And so that proves that what? That would prove that ONR is little ONR is a subset is part of the Lie algebra for big ONK, and so that's. But we already proved the other inclusion in general, so that would prove the case for R. And then again, just a little bit, about the geometry of what's going on here. So just taking a break from the proof for just a second here. R gamma ij of t, so you can think about the vector field generated by gamma ij, that rotates actually the subspace ei comma ej, the span of ei ej by angle t, and does nothing to the remaining basis vectors. So it's so-called, you can think of it as, this is the curve, it's cosine t, sine t, minus sine t, cosine t. This is a rotation which fixes the y-axis, right? So it rotates vectors in the 1-3 plane, where the 2 direction is the normal to the plane. And this comment just as well holds in n dimensions where the gamma ij is defined. Now that's part of what leads us to the geometric comment about how do you think about ON in general? It's a family of rotations in orthogonal it's a family of rotations in these orthogonal planes. But this is some of the details of that. Anyway, we'll leave the demonstration that the Lie algebra of ONK for the case C and H, this corresponding argument for C and H we'll leave to the reader in the case of the complexes and the quaternions, all right? Now, once we know that the Lie algebra of ONK is little onk, it follows that you can calculate the dimensions. And I think these are straight from TAP, so man, I just don't believe that. I mean, we just looked at, I must be missing something here, folks, I don't know. We looked at U2 over here, right? And U2, oh, okay, well U2 is four-dimensional. 4 is n squared. 2 squared is 4. I guess, yeah, he's got it. SP2 is 10, supposedly for the symplectic case, right? Remember SP2 is 10? So let's check, let's just do a quick check here on that formula. If I put in n equals 2, I get 2 times 4 is 8. 8 plus 2 is 10. Hey, well, you know what? I'm starting to trust those. So these dimensions came from counting the number of free parameters in the skew symmetric, skew Hermitian, and skew symmetric, the skew symplectic matrices respective. And that brings us to chapter 6. So I'm going to pick it up again there. Thanks.